Welcome VDSers. This video is on alignment in PyMol. The reasons we'd want to do an alignment are to compare two different structures. Perhaps we wanted to compare the structure of DHFR in humans versus that of bacteria. We could align these and see how different their shapes are. We can also use alignment to help us define the active site. We're going to go to virtual screening and using gold. Gold needs to know where the active site is. But if our structure is an apo structure or doesn't have any ligands bound, we may not know exactly where the active site is going to be. This can help us basically steal a ligand from another structure that does have a ligand bound. So often we call the empty structure the apo structure, and we call the structure that has all the substrates present the holoenzyme. So we can take from the holoenzyme, align it with the apo enzyme. As an example, I have a Staphylococcus aureus DHFR structure here, 2W9T. If we scroll down, we can see its resolution is 2.35 angstroms. When we go down to, here's the EC number, we'll use that in a second, 1.5.1.3. There's two chains present in this structure, but there's no small molecule components. That section is just left out here because this is an apo structure, or empty. Let's put this into PyMol. UW9T. And I'll expand this window just so we can see a little bit better. And we show the sequence viewer in the bottom right. We can see that there's two chains here. This is chain A and then chain B. So change this to chains. We have a chain, this is chain B, and this one over here is chain A. But we don't see any ligands. If we scroll further over, we see waters in red O's here, but we don't have any ligands present. So this is an apo structure. I look at this and I say, gee, I wonder where the active site is. I really want to dock this in gold, see if I can find any small molecule compounds to bind it. So let's go find another Staphylococcus aureus structure that has a ligand bound. So I want to use the advanced search feature in PyMol, in the PDB. Click on advanced search, and I'm given the option of several fields here. And this first field, what I want to search for is the, under biology, the enzyme classification number. I know that the EC number for DHFR is 1.5.1.3. I also know I want to search for Staphylococcus aureus structures, so I search under biology, source organism taxonomy name, Staphylococcus aureus. Pops up in the pull-down menu. I just click on that, and then I want to, these are both and, so both these conditions have to be satisfied. I also want to add the chemical component for a drug that I know fits into the active site of Staphylococcus aureus DHFR, and that's trimethoprim, and its identifier is top. So I knew that by searching before. So I have three conditions here. I count them in the bottom right. It says there's 5 structures. Then if I did click on the magnifying glass, it will show us all 5 of these structures. This one's a mutant version. This one has DHFR with NADPH and trimethoprim. This one has DHFR and trimethoprim. This one has NADPH and trimethoprim as well, and this bottom one is DHFR with trimethoprim. So 2W9H. This is good. Here's the structure, 1.48 angstrom. Here's the EC number just to double check. And then small molecules. We have 2 different small molecules here. Ethane diol is just kind of floating around in solution. It's not necessarily a ligand into the active site. It's used in the conditions used for crystallography. And then we also have trimethoprim, which is the drug that binds into the active site. So now I can load this one, 2W9H, into a PyMol window. We see it shows up in blue. If we scroll over on the sequence viewer at the top, we can see top is the ligand that's present down there. A little bit hard to see. What I want to do is I'm going to give it a selection name, top, and then I'm just going to color it kind of this kind of dark blue. So it's still going to be blue ish, so we know that it belongs to 2W9H. But what we want to do is get that top ligand into our active site of our apo form of the enzyme, which is the green one. These two structures aren't aligned at all. They're just kind of sitting in random positions in space. So let's align them. So I'm going to align 2W9H to my 2W9T. So usually a little bit safer to move the thing that you're not going to save to the thing that you are going to save. So the green one is the one, the 2W9T is the one I want to take to gold eventually. So I'm going to leave it in place and align the other thing to it. So it aligns, and it goes and aligns to the A chain of 2W9T. This is the A chain right there. And we can see now where the ligand sits in and can help us define where the active site is. The trick now is to be able to save the 2W9T and that top ligand. So the apo form of the enzyme and the top ligand, we want to save those as one file so we can take that to gold virtual screening. In order to do that, I'm going to separate out top as a separate object. I'm going to extract it as an object. And then now I need to rename this object. I'm going to call it object underscore top. So now that it's an object, it's going to be easier for me to save that with the 2W9T. I'm going to change my selecting mode to objects. I'm going to click on top, and then I'm also going to click on the 2W9T. So now they're both selected. I just did a regular left click on each of those, and this is the new selection here. So I'm going to rename that selection to W9T and top. So I have to have these as a selection in order to save them together in the new PDB file. In that new PDB file, I won't have the 2W9H structure in there anymore. I'll just have the ligand and the apo form of the enzyme. So here I'm going to go to export molecule, and then I can go down here and select anything that's been made into a selection. Since I can't control click and click on multiple things, that's why we had to save top and 2W9T together in a selection. Click on that, save, and I'm going to change. I have this on my desktop. Let's see. Scratch alignment. Okay. I don't want to save it as a CIF file. I want to save it as a PDB file. The 2W9T and top. I save that. I want to make sure and save my session real quick. Save the session. Now what I want to do is double check that I actually saved those two things together. So I go to File, Reinitialize everything. I'm going to go reopen that selection that I just saved, those two separate objects. I'm going to open PW9T and top. And now, so the sequence viewer, I can see that I have my two chains of the original apo structure, and now I have top sitting in the active site. I can go color this top again according to the way I had it before with the blue, kind of blue coloring there just to be consistent. And now I've got my ligand in the active site. I can take this to gold, and gold can use that to say, oh, this is the active site. This is where we're going to dock to. One thing I wanted to point out here is that this is a little bit unrealistic to have this this ligand so close to this this loop of the protein. So these amino acids in green So we can show those a little bit better. I click on one of these guys. So call this loop. And show the side chains as lines. So what we can see here is that these amino acids in this loop are basically taking up this space. It wouldn't be possible for a ligand to sit in the same space here. There'd be lots of clashing going on. What this highlights is the conformational changes that can take place between a apo form and a ligand-bound form of the structure. In order to see this really well, what we should do is go back and reload the original one with the ligand, UW9H. Reload that. I'm going to realign it. Align to molecule. So what we can see here is this loop right here is basically sitting in the place where the ligands would be. But in the other structure, the one that had the ligand bound, this loop, the loop is much further back. You can probably identify where this is. I'll highlight some of these guys. I'm going to call this loop bound. So this is a loop when the ligands are bound. I'm going to show side chains as lines. And we can see there's a big difference in the position of these loops. Another way to show this is to show the space filling version of this. So if I show this loop, or I'm going to show spheres. These spheres represent how much kind of space these atoms are taking up, and we can see there's basically no room for that this ligand to be present here when this loop is in the way, kind of filling up that space. We go back and show those as cartoon, it originally was, and show the other one, the loop where it's bound, show spheres. This takes up a lot of space as well. Oh, whoops, it looks like I incorporated the ligand into that definition. So I'm going to show as cartoon. I'm going to delete the selection and remake it. Look up here. Now there we go. A tab, rename loop bound, underscore bound. Show those as spheres as well. Show spheres as well. And now when we show the space filling spheres for the bound version of the loop, we can see that it leaves enough space for the ligand to be present. These spheres don't overlap with the space where the ligand is. And that's why this loop needs to be flipped outward in the ligand bound version as opposed to the bound version. It allows space for that ligand to fit in the pocket. Okay, so this is a exercise to see how we can use alignment and compare structures, and how we can use an alignment of a ligand in order to be able to take it to gold virtual screening. Good luck in your screening, and see you soon.